So, give a brief refresher of Whisper for people who might not have heard of it. So Whisper is sort of this part of this, back in the day you had this holy trinity with Ethereum, Swarm, and Whisper, sort of the compute, storage, and messaging. And Whisper sort of, it's sort of the messaging layer, and it's gossip-based messaging, but you can also look at it as kind of ephemeral key value store. And it has this sort of ambition to preserve some metadata and have this sort of darkness property, as well as being spam resistance for the use of proof of work. It hasn't seen a lot of usage, and it hasn't been developed a lot. I think the main users of it is most likely sort of the status app. And there's a few reasons for this. So first of all, it's using proof of work for spam protection, which is quite bad for heterogeneous nodes. So if you have a mobile phone, it's quite expensive to sort of do some proof of work, which means that you need to lower the requirement, and it makes it very easy for someone with a more powerful computer to sort of overwhelm the network. It also has a bunch of sort of fundamental scalability issues that we'll talk a bit about more detail later, but it has to do with sort of the lack of routing, how it's using Bloom filters, and so on. There's also no incentive to really run a node, and sort of this darkness property and the anonymity claims it's making are kind of not very rigorous, and it doesn't correspond to anything in academia, and to the extent that it is sort of privacy preserving in some way, it sort of quickly breaks down in production environments. And finally, sort of the specification is there is one, but it's not machine readable. There's differences between implementations, and it's not clear exactly what guarantees it provides. So what's good about it? Well, it's running in production. It's running on top of DevPTP. It is decentralized. You have this sort of topic-based messaging system, which you can use for decentralized group chat and public chats, which is what Status is using it for in production. It also provides some type of encryption if you don't have a layer that takes care of that. And it does provide some privacy guarantees, even though they are fairly weak. So last year, we were here at the panel together with NIM, Validity Labs, and Web3 Foundation. Back then, a lot of talk was about sort of mixed nets and these extreme privacy guarantees, and that's not what this talk is about, and it's also not what Waku is about. In terms of privacy guarantees and so on, Whisper occupies this kind of suboptimal spot. So this is this thing called an anonymity trilemma. There's 4 points here, but essentially you have strong anonymity, bandwidth, and latency, and you have to pick two. So if you want strong anonymity, you have to sort of sacrifice bandwidth or latency. And then the sort of fourth dimension is the user distribution, which if you have more users in a system, then you have sort of a larger anonymity set. And Whisper is kind of in a spot where you have very high bandwidth usage, but you don't get very much strong anonymity in return. And because of this high bandwidth usage, it also makes it hard to sort of scale the network, and that also sort of impacts things. So that doesn't mean that we are not sort of interested in this and sort of these types of mixed nets that are being researched by NIM and so on. But it's a matter of order operations, where sort of our priority is to support sort of the scaling of these protocols. And it's really it's quite difficult to sort of there's a bunch of unsolved problems when it comes to running these protocols on mobile phones. And Dean will talk a bit more about sort of what we mean by resource-addicted devices here.
So yeah, as said, we're probably the only people using Whisper right now, which is Status. And that's suboptimal because Status is essentially for resource-restricted devices. We define resource-restricted devices as devices which have generally less efficient CPUs, aren't able to have that much bandwidth. There's battery concerns, memory concerns, uptime concerns, etc. For smartphones, for example, the problem here is we're mostly offline. There's very short connection windows, so you can't, for example, sync a DHT. First of all, that affects battery usage. It also is impossible to do in like a 5-second window that you're in a messenger app replying to a text message. And limited bandwidth. You don't want something like Whisper, which has a huge overhead, where you end up syncing all this data over your 3G. It's just draining on your device. We wrote some scalability assumptions, which Oskar will talk about when it comes to Whisper.
Sure. So it's become this kind of meme that Whisper doesn't scale. And while the intuition is correct, it's very useful to be able to understand exactly why. And in order to sort of change the protocol in such a way that it could allow sort of a reasonable amount of users, we sort of decided to make like a theoretical scalability model for Whisper. And I'm not going into sort of the details of all of this, but essentially what we did is we just encoded best understanding of the protocol and how it behaves under reasonable assumptions. And what this allows us to do is that we can sort of, if there's something here that someone disagrees with, then we can sort of reason about that in isolation and play around with the model and have a very quick turnaround time in terms of the kind of changes we want to make that would have a big impact. So we encoded things such as how many sort of messages are floating in the system, how the bloom filter works. So the way bloom filters work in Whisper is that you sort of get some kind of plausible deniability because you listen to more messages than you actually want. Sort of how many duplicate messages you get, how often nodes are offline, and so on. And by sort of encoding these assumptions, we got this sort of model where essentially we have different types of cases, starting from sort of the most naive and then building up with more layers in terms of things that we observed or things that we intuited existed in a real-world production scenario. So this is a log-log graph, and you see on the x-axis is the number of users in the network, and on the y-axis you have receive bandwidth megabytes per second per day. And you see a bunch of the sort of graphs up here, and very quickly at like 300, 1,000 users, something like that, you quickly run into very high bandwidth consumption, which is a big issue on a mobile phone, especially with limited data plans. You see this line here, that's sort of the vacuum mode, and essentially a lot of that comes from the fact that it's using topic interest as opposed to sort of bloom filters directly, and that allows you, because with bloom filters you have this false positive rate, and that's sort of a function of all the messages that are floating around in the whole system. And by sort of being more direct about that, the system scales a lot better. There's also a bunch of other changes that Dean will go through. This tick here, where it increases again, that has to do with how the status app is using Whisper or Waku directly, and it's how sort of the topics are partitioned. But that's also deployment specific. Okay,
so now that we have this introduction on Whisper, let's quickly get into what Waku is. As said, it's a fork of Whisper, which is EIP 627. It's optimized for better usability for resource-restricted devices, so our main focus is lowering all these bandwidth problems and ensuring that it's usable on mobile phones. Because, as said, our users are mostly offline bandwidth-constrained smartphones. Like, we're trying to build this so that it's as efficient as something like WhatsApp. How do we do this? We add support for things like light nodes. So there are mobile clients which don't have to retransmit messages. They simply receive the messages which are meant for them. We have historic messages which you load from external servers, or mail servers as we call them. You do this by having your topic interest or bloom filter which you provide to the server, and it returns the messages which are meant for you. And we implement rate limiting, because proof of work, as previously stated, it doesn't work. Like, we'd have to lower the work required on a mobile phone so far, we'd have to lower the work so far that anyone could spin up an AWS server and just start spamming the shit out of all of our Whisper nodes. The trade-off here is metadata protection versus scalability. But as said, the metadata protection which you get from Whisper isn't very rigorous. There's like no academic study on how much it actually provides. So how we went about how we decided to do these Waku specs is we split up the spec into 3 separate parts. So we have the Waku spec, which is the main Whisper fork. Then we have things on the envelope data format, and then we have a spec for the mail server. So these are 3 separate components. One thing that was very important to us is that we formalize the specs more. Whisper doesn't do this right now, so we have things like ABNF grammars, which properly describe how the packets look, what is contained in a message, how it's serialized, etc. The entire spec is split up in capabilities. So a Waku node can have multiple capabilities, and nodes can choose which capability they support. So not every node is a mail server, for example, and not every node needs to be light client friendly. So you can choose which ones you implement depending on what you need. You can also choose which nodes you connect to depending on what you need. There's explicit security considerations and implementation notes in the spec, which is also something which is missing from Whisper, so that developers actually know what the security considerations are and how things are implemented or how they should be implemented, with examples leading or from all the implementations there are of Waku. What's interesting as well is we're compatible with Whisper. We do this through bridging. We can easily bridge packets from Whisper to Waku and vice versa. And we use clearer language, which we also don't often see in EIPs, meaning we follow RFC 2119, which has very clear definitions of terms like must, should, may, etc., so that our specs are fully understandable. Where are we now on this? So we've recently released our latest spec, v0.4, with all these necessary components, which should be going into status relatively soon. Nimbus and Status Go already implement this version. There's more details on the actual specs page on which versions they support and what capabilities they support. We made tweaks to expressing topic interest more dynamic and less error prone. So like, as said, this optimizes above the Bloom filter, or this is an optimization versus the Bloom filters. We have simulations supporting the theoretical models that we've built, which we use the Nimbus client for. As said, core implementation or core integration is a work in progress, and it's expected to be experimental in the 1.1 release of Status, meaning that users can decide on if they want to use Whisper or Waku, and we make those trade-offs very clear on what the privacy trade-offs are, etc. We wrote a blog post about that, and there's quite a lot of detail on that and like what we're doing right now and in the future, etc.
Cool. So we had this sort of theoretical model, but that's kind of living in isolation, and it's nicer to have some better sort of guarantees of this thing working out or not. So we made this simulation, which is actually running the protocol. It's written in Nimbus, and you have sort of these full nodes, and then we have Whisper-like node, sort of the previous protocol, and then we have Waku-like node. And you see here that we have maybe 10,000, around 10,000 of valid envelopes flowing around the system, and then a 10% false positive rate, which you see here. So that means that you get a lot of messages that are not for you. And then you have sort of one message for the Waku client. So there's a huge difference in terms of received bandwidth between the different sort of modes, from Waku to Whisper light node and then full node. You can also see that there's a bunch of invalid messages, and it has to do with the lack of routing in Whisper. So depending on topology, you're likely to get the messages multiple times. So in terms of sort of bottlenecks, we talked a lot about the sort of first one. This is the obvious one that you notice as a user, which is the received bandwidth for sort of mobile phones, which is sucks on a limited data plan. The second one, which Dean will talk a bit more, about more soon, is sort of the node discovery, because you sort of, if you're on a mobile phone, you need to find nodes that can help you sort of relay message to it and get relayed message from. And then the third one, which is something that we haven't directly observed, but very likely to kick in, is sort of the full node traffic. So even though you sort of solve the endpoints, sort of the mobile phones, and then you have all these other nodes, and you can find all these other nodes, you still have sort of the issue of traffic between these full nodes, because there's no real sort of routing. And that's something that's sort of in early work in progress. And it's likely that in future versions we'll move to some more structured kind of routing, some versions of Cademly and so on, but that's still, yeah, more to come on that later.
Yeah, so one of the things we did so that we can move away from this Cademlia rendezvous-like discovery bloat, which we were using before, is use EIP 1459, which is a DNS-based discovery protocol written by Felix Lange, which was done for Disk V5. It essentially stores a Merkle tree within DNS text records. And the nice thing about it is it adds authenticity to this. So the Merkle tree or the Merkle root is signed within the tree. So we know if some adversary changed DNS records because we know that the signature is not signed by the public key we expect it to, or we can easily check whether one of these leafs is actually in the root. This is super efficient because, as said, we just need to query DNS text records, which is a lot easier to do on a mobile device versus syncing with a Kademlia DHT. So what's next for us? We're working on improving routing, as previously said. We're working on a separate piece of work, which is we're trying to figure out better storage solutions. This helps us clean up the mail server situation so that we use some kind of decentralized storage solution behind that, and we're working on optimizing that for all these issues we have with low bandwidth devices, etc. Additionally, we're working on incentivization so that nodes are actually incentivized to store other people's messages, which is not the case right now. We're also working on better spam resistance, where we're looking into things like Semaphore, written by Barry Whitehat, which is a zero knowledge proof spam resistance mechanism, which we can probably use. And beyond that, or further down the line, what we will probably be doing is removing def P2P and switching it to a libp2p based protocol. This will allow us to use things like WebSockets, which will allow us to easily write browser clients, easier mobile clients, etc. For those of you interested, we publish quite a lot on our site, including monthly blog posts about our progress, what we're working on, along with all of our specifications. You can find those on our website. Are there any questions? Okay, thank you.